Hello, and welcome to this special celebration of UCLA's Galactic Center Group and its 25 years of groundbreaking achievements. I'm Gene Block, UCLA's Chancellor, and I thank you all for joining us. Under the expert leadership of its director, Professor Andrea Ghez, the Galactic Center Group has opened up the center of our galaxy as a laboratory for studying black holes and their role in the evolution of the universe. Some of you know that Andrea's initial proposal for telescope time at the Keck Observatory in Hawaii was turned down. She was told her research wouldn't work. Fortunately, she didn't get discouraged. She convinced those at Keck that her ideas were sound. Then she revolutionized her discipline with the discovery of a supermassive black hole at the center of our galaxy, and this past October was awarded the Nobel Prize in Physics. Among many other feats, her Galactic Center Group has also conducted the most comprehensive test ever of Albert Einstein's iconic general theory of relativity and published the results in the journal Science in 2019. The collaborative work of the Galactic Center Group is truly emblematic of UCLA's mission to pursue scholarship that increases our understanding of the world and our place in it. Even after 25 years and a Nobel Prize, the members of the Galactic Center Group are not pausing to rest. They are launching an ambitious program for the coming decade, and I know we're all excited to see what the future holds for this impressive team. I want to thank and congratulate Andrea and all the members of the Galactic Center Group on a quarter-century of successes, with more to come. I'm also grateful to all our supporters for your enthusiasm and passion. We cannot overstate the importance of your dedication to advancing scientific discovery. At a time when science is so essential for helping us navigate the major challenges of our time, your affirmation of the value of rigorous, fact-based inquiry is essential. I'm particularly grateful to Arthur Levine and Lauren Leichman and Astrid and Howard Preston for their early and enduring support of Andrea and the Galactic Center Group. I hope you enjoy the rest of this stellar program, and thank you again for tuning in. Now please welcome Dean of Physical Sciences, Miguel Garcia Garibay.
Thank you very much, Chancellor Block. Welcome everybody to the 25th anniversary celebration of the Galactic Center at UCLA. My name is Miguel Garcia Garibay. I am a professor of chemistry and biochemistry, and also the Dean of the Division of Physical Sciences, which is home to the UC Galactic Center and also to the Department of Physics and Astronomy that houses the center. Well, physical science at UCLA is one of the most accomplished units in our campus. We attract some of the best faculty, students, postdocs, and researchers to really tackle the most interesting challenges, scientific and technological of our times. Our faculty and students work to really advance science and to really also work on education and try to make education as available as possible to as many people, which we think is really important. We also count with some of the most accomplished inventors in our campus. And in addition to that, we count with the exceptional support of many, many alumni and friends of UCLA who really help us make everything that we do possible. Physical sciences actually is one of the things that I can tell you that I think puts it in context is that 7 of 8 UCLA laureates from the UCLA faculty are from physical sciences. So this includes Willard Libby, Donald Cram, Paul Boyer, and Fraser Stoddard, who have been recognized for their work in chemistry. We also have mathematician Alois Shapley, who was recognized for his work in economics. And then we have Julian Schwinger for fundamental contributions in physics. Now, of course, one of the things that we have most to celebrate is that the 2020 Nobel Prize was given to the director of the Galactic Center Group, our own Andrea Ghez, for her exceptional and really inspirational discoveries in astrophysics. Today, we honor the important part that the Galactic Center has had in the contributions of physical sciences over the last 100 years, which have really expand well beyond science and technology innovation. And we have to look at also the people. So the impact that the Galactic Center Group has had on people is just remarkable. There have been over 50 graduate students and postdocs that have been trained in the Galactic Center Group who have gone on to take leadership positions all over the world. And now they're guiding their own research, really asking some of the most interesting questions of our times. Not only that, but they are also inspiring a new generation of astrophysicists, which is truly remarkable. Another thing that I want to point out is that the Galactic Center Group has played a key role in exploring your universe, an event that is a shining star for UCLA. As many of you know, for the last 12 years, the first Sunday in the month of November, about a couple of hundred UCLA students and faculty welcome thousands of children and their families from the UCLA community and many others to experience online life science and hands-on experiments, really inspirational lectures, and have an opportunity to interact with our students and our faculty. We feel that our visitors feel empowered by the truth that science can be practiced and enjoyed by everyone, no matter who we are and where we come from. Exploring your universe would not be possible without the contribution from the Galactic Center Group. So last year, for example, we had to have Exploring Your Universe online. Now you might think, how do you translate an event that brings thousands of people to the campus and make it happen online? Well, it was very challenging, but it was widely successful. Not only did we have a large number of people from our community participate in it, but we actually had a significant number from across the country and from different parts of the world. I personally think that the event was so successful because, of course, we could celebrate Professor Guess's Nobel Prize. She gave an absolutely brilliant lecture, and she received the UCLA Science and Education Pioneer Award. So it was just a sensational event that gives you an idea of the type of engagement that our faculty, even our Nobel laureates, have trying to reach out to our community. So now, to speak more about Andrea's unparalleled contributions to UCLA and the world of science, we will have Arthur Levine, who chairs the Galactic Center Group Board of Advisors. Arthur and his wife, Lauren, have been truly instrumental in supporting the work of the Galactic Center Group. Arthur will be followed by world-renowned string theorist, physicist, mathematician, Columbia University professor, and co-founder and chairman of the World Science Festival, Brian Greene. And then we will hear from the brilliant and inspiring Nobel laureate director of the UCLA Galactic Center and holder of the Loren B. Lathman and Arthur E. Levine Chair in Astrophysics, our own Andrea Guess. So now I'll give the screen to Arthur.
Thank you, Miguel. I am absolutely delighted to join Chancellor Block and Dean Garcia Garibay in congratulating my good friend Andrea Ghez on her receiving the Nobel Prize. I have been a long-time supporter of her extraordinary research and have watched her over the many years and was not surprised when she won the Nobel Prize. I'm absolutely thrilled to support her, Andrea, as she continues her outstanding groundbreaking work from proving the existence of a supermassive black hole at the center of our galaxy to testing Einstein's theory of general relativity, as well as her current research on dark matter, which I think personally, discovering the structure of the universe as it relates to dark matter is one of the most exciting things Andrea's worked on. I'm sure these discoveries are going to be as or more exciting than the ones in her past, and I congratulate her on all her success and will continue to support her in all her efforts.
Andrea Ghez is one of the most inspirational scientists of our age. I mean, think about it. Albert Einstein, back in 1915, writes down the equations of the general theory of relativity. Just a year or so later, Karl Schwarzschild realizes that within those equations is a solution that should look like what we now call a black hole, a region of space where matter is compressed to such fantastically small size that the gravitational pull is so enormous that nothing can escape. Einstein himself doesn't believe the solution. He doesn't believe that these kinds of monstrous objects would actually be part of reality. Now, people debate this over the course of many years. Einstein writes papers purporting to prove that black holes are not real. And then Andrea Ghez comes along and has an idea for how you might actually prove the existence of black holes observationally. The idea being to look at the center of our galaxy where there was some circumstantial evidence that there might be a black hole, use high resolution optics that she would develop so that you'd have these crystal clear pictures of the center of the Milky Way galaxy, allowing you to track the motion of stars as they orbit the center, and through the motion of those stars prove that they must be orbiting around an object whose gravity is so powerful that it would have to be a black hole. Puts this idea forward. People think, not going to work. That idea, not going to bear fruit. But Andrea has the fortitude to keep pursuing the goal, keep pursuing this insight into the nature of reality, and is able to push the project through to a successful conclusion and give us the first real concrete evidence that black holes are real. Wow, what a story of discovery. What a story of inner strength to pursue such an enormous goal, even in the face of others who think it's just not possible. A goal that she and her team achieved, rightly awarded with the Nobel Prize in Physics. So it gives me such great pleasure to congratulate Andrea on the incredible science and this well-deserved recognition from the Nobel Prize Committee. Congratulations, Andrea.
Thank you, Brian. Thank you, Arthur. Thank you, Dean Garcia-Garibay, and thank you, Chancellor Block. It gives me just great pleasure to celebrate with you today our 25th anniversary of the Galactic Center Group. Let me just get this going here. This endeavor started 25 years ago, just as I joined the faculty at UCLA. And why I was so excited to have a position at UCLA was that I was interested in using these telescopes and developing new ways of using these telescopes to get the sharpest images ever possible from the ground or space. And this was possible because Keck themselves, these telescopes are the largest telescopes in the world, and they're co-owned by the University of California and Caltech. And the reason why I was so excited about the possibility of using these telescopes in a new and different way is that I wanted to address this question of, is there a supermassive black hole at the center of our galaxy? And intrinsic in that question is the question of whether or not these monstrous supermassive black holes exist in the universe. And I was delighted to come to UCLA because not only did we have access to these telescopes, but there were others on the faculty who shared parallel interests in the center of the galaxy, in new technology. So this is a project that I've done in collaboration with my colleagues, Mark Morris and Eric Becklin, for the last 25 years. And along the way, we have also worked with a large number of other professors for what now seems like a long time. So at least another decade, including Professor Tuan Do and Professor Jessica Liu, along with a host of students and postdocs. Okay, so why is this an interesting question? Black holes, as Brian Greene just so eloquently shared, black holes are intriguing because they're objects that, in a sense, defy some of our basic understanding of how the physical world operates. So Einstein, who is so famous for his theories of gravity, predict that these black holes should exist, that they're objects whose pull of gravity is so intense that nothing can escape them, not even light. So this event horizon, or the Schwarzschild radius, is this magic or abstract point at which you can't collect any information. But it's also the magical point at which, if you can press an object down to its Schwarzschild radius, gravity overcomes all other known forces, and the object becomes the infinitesimally small object known as a black hole. So the fact that it becomes infinitesimally small also points to the fact that we don't know how to make Einstein's theory of general relativity work with quantum mechanics. It explains why black holes presents this conundrum. So in a sense, they're intriguing objects because they highlight an opportunity to learn more about our fundamental understanding of how physics works. The supermassive variety of black holes, those that are 1 million to 1 billion times the mass of the sun, are also intriguing because we think these black holes reside at the heart of galaxies. This is a galaxy that would look very much like our own if we could get back out and look back inward. And we think that the supermassive black holes are intimately tied to how these galaxies form and evolve. So if we want to understand these fundamental building blocks to the universe, it's essential that we understand the relationship between these black holes and their host galaxies. So if we want to understand supermassive black holes, our galaxy affords us the best place to look because it's the closest example of the center of a galaxy that we'll ever have to look at. The next closest galaxy is 100 times further away. So this is a lovely photo that's taken from the side of Mauna Kea on the Big Island of Hawaii. And we see the plane of our galaxy. So our galaxy is a flattened disk-like structure. Since we're looking through it sideways, we see the band of light that's all the stars in our galaxy. Because there's also a lot of dust in our galaxy, we see a lack of light going through the middle. And that lack of light comes from dust. Dust is very good at absorbing optical wavelengths, which is what our eye detects. But it turns out that infrared wavelengths, which is what UCLA is so good at, infrared astronomy, infrared light can penetrate through the dust and we can see to the heart of the galaxy. So the fact that UCLA is very good at the development and the infrared technology and methodology really makes UCLA an ideal place to carry out this research. Now, the original idea of finding this supermassive black hole was to look at the motion of stars, to watch how they move under the gravitational influence of the black hole. And stars are expected to move under the influence of the black hole, very much like planets orbiting the sun. These stars orbit the center of the galaxy, no matter what's at the center, because of the gravitational influence of whatever's inside it. So each orbit tells you the amount of mass that's inside its orbit, and the radius tells you how small a region that you've confined it to. So to show that there's a black hole, you want to show that there's a lot of mass inside a small volume. And when we first set out to do this project, we had much less ambitious goals than seeing the whole orbit. We were just trying to see how things moved on the plane of the sky in little line segments. And as Chancellor Block pointed out, even this simple idea was turned down because there was skepticism of whether or not our new techniques for using the telescope, the Keck telescopes, would work. And if they worked, would we see stars? And if we see stars, would they move? The reason the Keck telescopes were essential for doing this work, or why they were the ideal place to do this, is that the larger the telescope, the smaller the scale that you can in principle see. if you correct for the distorting effects of the Earth's atmosphere. So the Earth's atmosphere will blur our images of astronomical sources. We spend a lot of time thinking about how to overcome that effect and to achieve the sharpest images so you can see the stars that are as close to the heart of the galaxy as possible. This animation shows you a little bit about how this technology works, or rather the outcome of this technology. If you don't have this kind of technology, you get blurry stars, and if you have something that allows you to correct for the blurring effects, you actually see stars. We think the black hole is located in the heart of this, or in the center of this box. So it's these stars that we want to both image. So as you can see in this, this animation, the technology did work. And in fact, the way we make these images has radically changed over the last 25 years. So this is a project in which time helps you because the orbits have motion. So the longer you wait, the more precise your measurements get and the more you see about the orbit. But also the technology and our ability to even see was changing dramatically over the last 25 years. So I have to say this project has been like surfing a wave of technological development that has opened up new science with every step forward in the technological development. Without going into any detail about how these technologies work, I'm going to show you a movie now of how these stars that are in this box, but actually it's a box, the next box that you see is going to be a fourth of the real estate. So remember, this original skepticism was that we wouldn't be able to see any, make the images, that we wouldn't see stars and we wouldn't see them move. So I have to say this is a movie I could watch for a long time. It gives me incredible satisfaction and really represents the tremendous success of this project. The first 3 years of it were all we were thinking about 25 years ago. 25 years ago, when we were a team of just 4 people. Mark Morris, Eric Beckland, my first grad student, and myself. And we were just interested in seeing the arcs. But at that point in 1998, there was a tremendous amount of skepticism about whether or not it was the black hole that was moving these stars around. And what that told us is that we had to keep going. And you know, if there's a black hole at the center, that these stars will ultimately start to curve. So fortunately, we were able to get the telescope time and see the first deviations from how these things move on straight line in roughly 2000. And at that point, we understood that orbits were possible. So I have to say, in the early 2000s, that was an incredible moment of understanding how much more powerful this work would become. And in fact, even then, we didn't understand how many dimensions this would blossom into. So the orbits themselves, and in particular, you probably noticed my favorite star, whose name is SO2. It probably needs a better name, but it goes around in it was the one that went around in 16 years. And what that star tells us is that there's a 4 million times the mass of the sun inside a very small volume. So at the outset of this experiment, we knew that there was 4 million times the mass of the sun inside a circle that whose size is shown here. So it's huge. There's a lot of stars and gas and dust inside this circle. So you can't claim that it's a black hole. But what this work has done is to confine that mass to a volume that's a factor of 10 million times smaller. So in a sense, you can say that this has increased the evidence for the existence of supermassive black holes by a factor of 10 million, moving the idea of supermassive black holes from a possibility to a certainty, as we've confined that 4 million times the mass of the sun to a scale that corresponds to roughly the size of the solar system. Now, today, that leaves us, that statement alone, that's really what the Nobel Prize is all about, having gone from just velocities the first 3 years, which moved us a factor of 1,000, and then the orbits, which gave us another 10,000, factor of 10,000, that got us to the 10 million. And today, that gives us, with that factor of 10,000, the strongest evidence today for the existence of supermassive black holes, not only at the center of our own galaxy, but anywhere in the universe. So now we have a wonderful laboratory to turn this all around, to understand the physics and the astrophysics of supermassive black holes. And I'd like to start with the astrophysics. And by that, I mean the astrophysical role that black holes play in the formation and evolution of galaxies. And this is an aspect of this project that is particularly delightful because it's the area in which almost every prediction that you could make for what we should see around the black hole has turned out to be inconsistent with the observations. So from my perspective, this is like being a kid in a candy shop because it's just opening up a large number of questions in a wide variety of astrophysical domains that can be addressed with this data set that we've obtained for asking the original question about the existence of the supermassive black hole. This animation, which shows you the three-dimensional motion of the stars that we've been studying, and it pulls back to give you that 3D sense, highlights three of the surprises. And so there are three new directions for our research. One is that around a black hole, you don't expect to see young stars. Black holes have these large forces, and in particular tidal forces, which tend to tear things apart, which really should suppress star formation from happening. In other words, baby stars shouldn't be in this region. It's a very hostile region to star formation. And yet the young stars are the aqua blue things in this animation. So in fact, they're the dominant population that we see. So I call this, or we call this, I should say, the paradox of youth. How do you get star formation happening in a region that's very hostile to star formation? And in this animation, hopefully you'll see that the orbits of these stars start to line up as you pull back. And in fact, it looks like a scaled up solar system. So this aspect of the work has just wonderful connections to people in our department and elsewhere who are studying the formation and evolution of planetary systems. So this is just as, because it really exhibits a lot of the same structure, and we're learning a lot from that in terms of thinking about how do these young stars form. The next mystery is that there should be lots of old stars. Old stars have a lot of time to congregate around the supermassive black hole. The old stars are the orange stars. There are very few there. So that's mystery number two. And it's an important mystery because the congregation of old stars, which are quite bright, are how we often is a signature that we use to look for supermassive black holes at the hearts of other galaxies. So the fact that we have a black hole and don't see that intense concentration of old stars is an interesting mystery that has implication well beyond our own galaxy. And then the last mystery in this animation, and in fact, one of my favorites today, are the magenta stars, the pink purple stars. These are objects that are actually being torn apart as they make their closest approach to the black hole. You see them as they make their closest approach, develop these tails. It's the first time anybody has seen these spatially resolved, what's called tidal tails, these interactions with the black hole. And we think that our current theory for how these things are forming is that the black hole may be forcing pairs of stars to merge. And this is intriguing because it may be lighting up a physical process that may explain some of the mysteries that are observed with the gravitational wave detector LIGO. So in my mind, it's always fabulous when different technologies that give you different windows into the universe can help you, or can help you understand the mysteries that have been uncovered with other techniques. So let me leave that, although there's a host of other things that could be said. This has provided lots of new projects that have been the basis of a lot of PhD projects over the years. But let me now turn my attention back to the black hole itself. And in particular, the idea that once we have full orbits measured, we are now well positioned to do new tests of how Einstein's theory of general relativity works in the environment of a supermassive black hole. And there are two in particular that we have focused. These are the first two that have been possible or in theory possible. The first one is how gravity, and in particular, how Einstein describes the mixing of space-time, or you could say the warp, the fact that space-time is warped, which is the mixing of space-time, affects how light travels from the object itself. So the star is the black hole. This is the orbit of SO2, makes it from well down in that gravitational well to our telescope. And there's an effect called the gravitational redshift that should happen. So let me see if I can show you in more detail on this next slide. So the gravitational redshift is an extra shift in the wavelength of light, which is what we use to measure how things move towards you and away from you, as the star dips down into this stronger gravitational field near the black hole. So the prediction is there should be this extra blip. And you see it at closest approach. So you first need a full orbit just to get a seat at the table. And then the next time it goes around, you get to make this measurement of the gravitational redshift. And I have to say, this happened in 2018. And for years, the team was 2018 or bust. And 2018 came, and it was an incredibly exciting year for us. And sure enough, that signal just beautifully emerged, this signal that represents the fact that the photon has to lose energy as it climbs out of the gravitational well in the way that Einstein predicted. So this one confirms Einstein's ideas. The next one is more intriguing. And again, for me, it's like that feeling that came about from the unexpected astrophysical results. We're seeing things that are not what we predicted. So the next probe is to watch how this object itself moves through space-time. And the prediction is that the object shouldn't come back to where it started, and it should precess like a kid's spiral graph pattern. So it should overshoot. In fact, this signal should emerge after you go through that first you go all the way around. The next time you go through closest approach, you get the redshift, and then after that should emerge the signal of the precession of the orbit. In other words, once again, you need to know the shape of the orbit. But what's being seen is that in fact the orbit is precessing, but it's precessing in the opposite direction, and at twice the rate. So this, again, is when life gets super interesting, because you have to think about what could it be? Could it be your analysis, in which case it's a colossal mistake? And when you have 25 years of data that you have to put together, you have to think about the accumulation of small mistakes that could amount to a signal. But if we take the leap of faith that it is physics that's emerging, it's not the physics we expected, but it could be consistent with the presence of dark matter at the center of the galaxy. So on the x-axis is the mass of the black hole. On the y-axis is how much extended mass that would have to be dark is surrounding the black hole, but inside SO2's orbit. So this is exciting, but still early days. But it is the thing, I have to say, that is getting me up in the morning these days to ponder how can we take the next steps to convince ourselves that we're on the right path. The visual I have here about what we're doing today, it's like going around kicking the tires on your car to find the weakness, because before you publish such a result, you have to make sure that you're right. Now, all of this becomes easier with the next generation of technology. So we're also in collaboration with Keck Observatory working on the next generation of how these things work. The techniques for correcting for the Earth's atmosphere, taking out the blurring effects of the Earth's atmosphere today rely on a single laser being shown up to the upper stratosphere. And in fact, a single laser only allows us to correct roughly 30% of the light. So today we're working on a system that launches multiple lasers. And that's essential if we want to think about the next generation of telescopes. So the Galactic Center team is now a key science project for both the development of new technology on the Keck telescope, as well as the development of technology for the 30-meter telescope. So this is what the UC system is engaged in after Keck. And its diameter of its mirror is 30 meters rather than the 10 meters for the Keck telescope. So this is an incredibly ambitious program that the Galactic Center Group team is taking a leadership role in. Going from left to right, the left is how these images look today without making them pretty, just the very central part. The middle is how it would work with the new technology, multiple lasers. And then the 30-meter telescope would allow us to see far more. I think it's important to realize that today we're only seeing the tip of the iceberg. We only see the brightest stars, and the fainter stars are below what we can see because things just become too faint and too close together to resolve. So all of this began, I want to come back to the collaboration with just this wonderful team of Eric Becklin, Mark Morris, and a single grad student along with myself. And today, this project is now a close collaboration of 30 individuals who are responsible for the acquisition and development of the project, and a broader collaboration of about 100 people from around the world. Today, I have to say, one of the things that I'm most proud of what we succeeded in doing over the last 25 years is not only in collecting a data set that is quite unique and remarkable, but also in having a team that we've succeeded in keeping intact for the last 25 years, and that is extremely well poised for the next 25 years. And so with that, I'd like to end with, if nothing else, I hope I've convinced you that there is a supermassive black hole at the center of the galaxy, and that we have not only answered the questions that we set out to answer, but uncovered questions that we didn't even think to ask. Thank you so much for your attention.
Well, that was a beautiful talk, Andrea. Thank you so much. I also want to thank everyone for joining us, taking time away from looking at their screens to look at their screens. But of course, the content here is perhaps a little bit different, talking about these deep issues of Einstein, gravity, black holes. And we'll take a couple questions in just a moment from some of the folks that are watching this live. But Andrea, I just want to ask you, the last 25 years can really be viewed as an incredible triumph for Albert Einstein. I mean, we all know Einstein was this genius character, but even ideas that he was uncertain about, I mean, going back to the idea of the cosmological constant, this energy filling space, he erased it from his equations, and ultimately in 1998, we found evidence that it's real. The idea of gravitational waves. Einstein himself didn't trust that prediction from general relativity, but now with LIGO, as you mentioned, we know that gravitational waves are real. Black holes, again, did not trust the mathematics that was coming out of his own theory. And now you and your team and others as well have given this really overwhelming evidence that black holes are not only real, they're probably commonplace out there in the cosmos. So now you're on the cusp, potentially, of finding something that may not agree with Einstein's ideas, right? I mean, Einstein, the first evidence for his theory came from the precession of the perihelion of Mercury. You're looking at the precession of the motion of stars around a black hole. You're now trying to explain it invoking dark matter to kind of make Einstein's theory work. At what point would you say, we have finally found something where Einstein's ideas really themselves need modification?
Well, the good news for Einstein is that he doesn't have to be wrong for this to hold up. So the fact that we're seeing things rotate at twice the speed in the opposite direction could mean that there's just something on top of Einstein's ideas. And in fact, for that really points out the importance of using more than just our favorite star, SO2, because you really want to look at or control for more than one possible process that's ongoing at the center of the galaxy. So in other words, you could think of the dark matter as really having a signal that drives you 3 times the rate, because there's still the Einstein's version that's pushing you in the other direction. So it's an interesting it's an interesting moment. And I think this is, as a scientist, one of the points that I find most fascinating, because you have to think about how do you design your next experiment to figure out or tease out what's actually happening here.
Right. You know, it's a wonderful story that you've recounted, and others in some of the preliminary remarks made reference to, that you put forward this idea. Initially, it was rejected, but you came back in full force, and as we know, ultimately made it work. A question I have is, if you're willing to go there, did that rejection shake your confidence at all? Or was it just like, I'm not going to listen to those people, I'm just going to go forward? Or was there a sense of questioning yourself when that rejection took place?
I think, you know, I think it's an important question, and about how do you overcome the bumps along the road? Because of course, in life and in research, we always experience those bumps. I think in this case, I had enough experience with the technique at other telescopes that I was quite convinced that it would work. But I did have to convince a group of scientists that weren't used to thinking about what this technique could do, that it was right. So in a sense, the challenge was going and convincing people and convincing yourself and writing a better proposal. I mean, the wake-up call was it wasn't communicated well enough. So yeah. I mean, and I also think that part of this is I had wonderful collaborators. I mean, I think it's part of the team aspect that makes it, you know, you go back and you convince yourself, and together you can go forward.
So this is a project that was a culmination. I mean, the result that there is this black hole of a particular size, it's a culmination of 2.5 decades of work. So presumably, little by little, you started to get more and more convinced of the kind of result that you were heading toward. When did you actually do the measurement and calculation, put it all together, and you say, it's a black hole? You know, the mass and the size are such that we don't have any other candidate to explain this. Was that toward the very end of this project, partway through?
Well, it was when we hit orbits. So when we had velocities, which was the first 3 years, we certainly took a leap forward in terms of improving the evidence by a factor of 1,000, but there were a lot of ways that people could shoot arrows at it, and they did. And that's the job of science. I mean, that's the scientific process. So in some sense, it said, at that point, we were aware that you could go further and see if you could see the accelerations. Once you get to the accelerations, you know that the orbits are short. And that was key, was showing that the orbits could be you know, shorter than a human lifetime, reasonable to follow, because of course, you know, the sun takes 200 million years to go around the center of the galaxy. You're not going to follow that. So I think it was when we got to orbits that we were really convinced, and we convinced the community. There were no more pushing back. So the velocities, it was pushed back, accelerations, it was pushed back. But by the time, and this was our result for that was published in 2003. So early announcements in 2002. But even at that point, we were still looking forward, because that's when it was clear that we could get to these new tests of gravity. So it just shifted. You know, you could see forward that it was going to get even better.
So, but had the orbits been such that they were a factor 4 or 5 longer, that would have put you in a kind of strange quandary, right? I mean, would you have carried on with the knowledge that the glory would have been bestowed upon the next generation of scientists?
I don't think we could have convinced the time allocation committee to give us the telescope time. I mean, that's precious time. And so I would have happily done something that long, but you know, I think it really speaks to why we could break through with Keck. You
Right.
needed that resolution to get down to such a close scale that the orbital timescales were short enough.
Right.
And getting to the 30-meter telescope brings it even shorter.
Right. So there are a couple of questions from some UCLA alumni I wanted to get to. Two similar or related questions, I really should say. One from Gary Struck, and apologies if I'm pronouncing your names incorrectly, and Bob Lehman. they ask about the size of the black hole at the center of the Milky Way galaxy and wonder why ours is so puny, 4 million, as opposed to the billion solar mass black holes that you find in some galaxies. And the second follow-on question to that is, can you give a sense of how such a supermassive black hole forms and its role in the formation of the galaxy itself?
So this is getting at the relationship between black holes and galaxies. So I'll just step back for a second and say that our understanding of that has evolved a lot over the last 25 years as well as a community. So when we were first publishing our results on the velocities, people used to ask which came first, the galaxy or the black hole. It was like the chicken or the egg problem. And of course, as a community, we had lots of explanations for both of them. But what we understand today is that there's a relationship between the mass of these supermassive black holes and the mass of the central part of the galaxy known as the bulge, that the black hole mass is always 0.1% of the mass of the bulge. So to answer the first question, our supermassive black hole is puny or small on the scale of supermassive black holes because our galaxy is relatively modest. It scales very well with this relationship. And the realization that there is such a relationship of things that are so different in scale over time scales, even from the early universe to the present universe, means that whatever formed the black hole had to synergistically form the galaxy, and that there's some feedback at work that keeps the growth of the black hole and the growth of the galaxy in lockstep. And so in some sense, that's the opportunity here to understand the environment, to look at these and to unpack these physical processes that people are starting to play with to explain how this feedback mechanism works. And that's also what makes it so entertaining and interesting, that the outcome of these models are inconsistent with what we're actually seeing.
So do you think that these really supermassive black holes, that they form through the merger of lower mass black holes, or they just have grown in size from some primordial starting point and have gotten to the size that they currently have?
Right. So there's, one of the predominant ideas about how galaxies grow over time is mergers. So we're, for instance, on a collision path towards Andromeda. Andromeda has a supermassive black hole, and ultimately the two galaxies will merge. They'll sort themselves out to be a bigger galaxies, and the two black holes will spiral down to the center of the galaxy. The most massive things tend to be located in the center. So they'll merge to become a bigger black hole. So it is certainly one of the dominant processes we think is the merger of galaxies.
Yeah. So we'll one day be Milkomeda or some such name, or Andromilky, or some combination of those. Bob Weeks, another alumni, asked, what is it that most excites you about the field of astronomy right now?
Well, there's the local and then the global. So let me answer it globally. I think what excites me so much about astronomy today is how much technology is driving it. We are just in a moment of technological explosion that is pushing forward, that the astrophysical discoveries just follow suit. So the fact that we can now detect gravitational waves after 40 years is phenomenal. That we can combine radio light from telescopes all around the world to look at the light around a black hole at radio wavelengths. To the 30-meter telescope, where we can do things like look for signatures of life elsewhere in the universe. It is just remarkable. It's rare, I think, that in a field. So much of what I taught in astronomy, intro astronomy, for those of you who remember Astro 3, is 20 years ago, is incorrect. We've really upended just our basic understanding, or even to look back to what was our understanding of the cosmos when UCLA was first founded. We're just celebrating our 100th anniversary 100 years ago. In fact, people were just starting to think that the universe was beyond our Milky Way. So that's rather amazing in terms of the acceleration of our knowledge of this immense universe in which we live.
So there are two qualities of our current picture of the universe that people hear a lot about, and there are a number of questions about that. I'm going to kind of combine them together into one, if you will. We speak of dark matter, matter that we believe is out there not giving off light, but we believe we have evidence for it through the gravitational force that it exerts. Dark energy, an energy we believe that's out there that we do not see, that we believe we have evidence for regarding how it has affected the expansion rate of the universe. Does it bother you at all, especially as someone who spends time looking at things in the cosmos, that such an essential part of our theoretical description of the universe involves things that we have no direct evidence for? No one's ever seen dark matter directly. No one's ever seen dark energy directly. Does that bother you? Do you think that will change? Could it be that there is no such thing as dark matter and dark energy? We've been fooling ourselves.
Oh, well, that's such an interesting question. I guess how I feel about dark matter and dark energy are two different categories. Dark matter, I guess I'm a big believer in, the laws of gravity. That seems to, the way things move seem to reveal this stuff that we can't see. It's still matter, has a gravitational interaction that we can understand. So in a sense, that doesn't present too much of a mystery. The dark energy, however, is the big, we don't even understand the physics that could give rise to this. I think this is we think it's 75% of the mass energy balance of the universe. That says either we really, we're missing a big piece of physics, or in the same way that I was describing, you really have to understand your measurement. There might be something how we've come to this conclusion. We're depending on a story that's built on itself. So it's the thing that I think we should constantly be asking ourselves. How do we know what we know, and where are the weak links?
Let me finish up with a couple of questions. There are a number of non-science-y questions that people in the chat are asking. And let me just sort of put them together. Questions asked by Dave Jones, Paul, John, Petrashko, Jennifer Pulakidas, Julie Meebane. Again, sorry if I'm mispronouncing your names. But they bring up a number of relevant issues to life on planet Earth today. We are in the midst of a pandemic. There's a great deal of political discord in the world. We are spending time, at least we have been, on building a space force. There's shrinking federal support for the kinds of research that we're talking about. You have had direct relations with these things because of the protests on the big island of Hawaii. So, number one, are you optimistic that we are heading in a direction that will take steps toward resolving these issues? And number two, is there any direct way in which your work at the Galactic Center, obviously you've revolutionized our thinking about the cosmos. Is there anything there that can help to revolutionize our thinking about ourselves down here?
Okay, so let me make sure I understand how you've wrapped those questions up. I'm optimistic. I'm a Bruin. I'm always going to be optimistic. I think basic science is so human. It's what makes us, in some sense, so successful as a species, is our curiosity and our ability to try to understand more deeply, more powerfully, our position in the universe, or what our capacity is. So I think as a society, it's important that we invest in science. I also think it's important that we invest in science that inspires us. that, and everybody's looked up and had curiosity about the universe. It's really hard not to be engaged by that sort of fundamental, I mean, it's fundamentally a very humbling question. You know, we're kind of small and insignificant compared to the cosmos. So I actually think astronomy has a special role within the sciences of public engagement in being a science that people are interested, curious about, and that you can talk about the scientific process and how we understand what we understand. The importance of disagreement or discussion to understand, you know, to come to a deeper understanding of what we know. So for those reasons, I'm actually quite optimistic about the future of both science and astronomy.
Yeah, I would certainly agree with that optimistic perspective. And I just would remind folks that are watching that, you know, supporting this kind of science is so vital. It's so exciting to learn things about the cosmos. Note that there's a silent auction that is going on or will be going on shortly. I have it up on my screen right now. A lot of cool things. You can have a dinner with Andrea Ghez. How many Nobel laureates do you get to have dinner with? That's very cool. Catherine Opie, beautiful photographs that you can bid on. So please, everyone should go and be generous with your support, as clearly supporting this kind of science is so vital to, as Andrea says, what makes us human. We are a species of explorers. So again, Andrea, thank you so much for this discussion. Thank you so much for the spectacular work. Congratulations again to you and your team on the Nobel Prize. And with that, I will give it back to Dean Miguel Garcia Garibay to take it from here.
Well, thank you, Brian and Andrea. I really enjoyed your conversation and the questions from our audience and the answers that Andrea gave us. I'm still thinking about it. I mean, you know, I don't think you need to be a scientist to realize that when you have a thought, an approach, an experiment that in 2 steps improves what you want to do by a factor of 10,000, so that it combines to 10 million, that's just absolutely brilliant. So, you know, that I think that's something really, really to think about, and it's just amazing. The other thing that I just thought is that, you know, our universe is agreed to be about 13.8 billion years, 13.8 billion years. And the galactic center in a mere 25 years has helped us really understand the universe so much more than we did before that. So imagine that what can happen with your support, with all of our support. So institutional support, you know, federal support, state support, but the most important one is the support of our community. I think all of us can play an incredible role on that. So before we conclude this portion of the program, and transition to the online auction, I want to take a moment to thank the entire group of supporters over the last 25 years who have made this work possible. And you see this incredible list here. I think, you know, we can say that every one of you have really contributed to a better understanding of the universe through the Galactic Center. And I think that is just sensational. Please join me in sending your our immense gratitude and virtual applause to all generous individuals and foundations that you see here. We're truly grateful to our steadfast supporters, the Star Society members, the GCG Board of Advisors, many foundations. So thank you all